This is Chapter 1, The Nature of Geology, Lecture 2. We left off on this diagram. Let's move now to a familiar environment and think about what types of materials we can find here. Earth materials. Starting with glaciers. That's ice. By definition, a glacier is ice that has survived multiple seasons and not melted. So up in the mountains is typically where we'd find a glacier. They carry all sizes and shapes of materials, including large boulders and smaller rocks as well, and sediments. Rivers carry silt, sand, and cobblestone, all sizes of sediment. Steep mountain fronts here have a lot of large angular rocks and sediments, which may be deposited later into a lake. Sand dunes, nearly all sand-sized sediments. Many beaches, of course, are mostly sand, but some can have rounded stones or angular stones, depending on the source of material that we have in that specific area. As we go further offshore, we can expect smaller sediment sizes like mud and the remains of sea organisms. Rocks formed in these surface environments are called sedimentary rocks. So let's look at this steep mountain front. The sediment that is produced from erosion off of this rock is large, angular, and we call it poorly sorted. And sorting refers to the differences in grain sizes. So when there's a huge difference in the range of sedimentary grain sizes that you find, like there's a lot of large ones and then a lot of small ones, we call that poorly sorted. If all of the sediments are the same size, we call it well sorted. This all moved under the influence mostly of gravity. With sand dunes, this is well sorted. These are all pretty much the same sediment size. It's sand sized. It's moved by wind. The wind is strong enough to move these particles. If there's anything finer than what you see here, like smaller, it's going to move out of this environment. We see it with the Sahara Desert every year. In fact, that material travels across the planet. This is a beach environment. The sediment here is rounded because it's been eroded over time. There's a lot of things that aren't quite the same size. I'd say it's moderately sorted to poorly sorted. We have a Sharpie marker here for scale. Of course, some beaches are mostly sand, where others are mostly stones. It just depends on the source of sediment and how long it's been there. Over time, this will become sand-sized. Just give it time. And now we're looking at rocks formed from magma. So volcanoes can erupt, of course, and ash comes out. It falls back to earth and it solidifies into rock. So volcanic ash forms rocks. Lava coming out of a volcano, it solidifies into rocks. But magma that doesn't reach Earth's surface cools and becomes rock under the Earth's surface. Heat around the magma chamber can bake or change nearby rocks by contacting it. And then we have forces deep within the Earth. They squeeze and transform a rock into a new kind of rock. We get some distinctive rocks forming as well when hot water cools, either on the surface, in hot springs, or at depth. And those are hydrothermal rocks. But a rock formed from magma or lava, igneous rock is what we call that. Here's a nice example of an explosive eruption. we can see earth falling back down to earth or surging down the side of the volcano. These are also igneous rocks, but we call them volcanic rocks to be more specific. Here's more eruption. We're not seeing any ash associated with this, not much that I can see here at all. This is a volcano that produces lava that flows onto the surface. Again, igneous rocks. This is a Hawaiian volcano. So again, with this diagram, we have heating near magma, perhaps increased temperature and pressure. If a rock is changed by heat and pressure, we call that a metamorphic rock. If a rock is precipitated or forms out of hot water, a solution of hot water becomes supersaturated and the minerals recrystallize from that hot water. We call that a hydrothermal rock. So the four major rock types that we're discussing in this class are sedimentary, igneous, metamorphic, and hydrothermal will give it the fourth category. Usually you only hear the first three. So a metamorphic rock, it began as some other type of rock, but something called deformation squeezed the rock, folded its layers, changed the way its crystals appeared, and it is now a metamorphic rock. This one began as an igneous rock. So with hot water, this is Yellowstone, you get hydrothermal rocks. Those rocks form where hot water is cool and minerals precipitate, like this hot spring. Some geologists might say these are metamorphic rocks as well, but I'm going to separate them in line with what the book says. A profound question is, what can happen to a rock? This is the rock cycle. We'll start with weathering. You have a rock, and weathering or erosion can mechanically break apart a rock, or it can chemically alter a rock exposed to sunlight, rain, wind, plants, animals, anything like that. We're going to have loose material or sediment. It's then eroded further and transported. Where it's deposited, this is at the mouth of a river or a river delta. It may then, after deposition, it becomes a sedimentary deposit. It can be buried and compacted. We call that lithification, where it becomes a sedimentary rock. And then it can be buried, of course, and sediments can be uplifted after burial without anything else happening to them except lithification. But buried rocks can also be heated, deformed, and converted into a new kind of rock, and we call that metamorphism. Of course, uplift at any time. That's our off-ramp for that. If a rock is buried and exposed to a high temperature, it can melt, and then melted rock can cool and solidify either at depth or by rising to the surface as an igneous rock. And at any point, they can be uplifted, of course, and weathered again, and we begin the cycle again. So that's what can happen to a rock. Well, look at this landscape. We have a few different types of features, including fractures, vertical fractures here. The point is that the hill has multiple parts. There's different ledges, different colors. Those are different layers within the rock unit. We also call this an outcrop. Some of that color looks to be a stain on the outside of the rock, like right about here. And of course, there are these vertical fractures. We have some corners that are a little more rounded versus some that are more angular. And at the base, there are loose pieces here that are not part of the solid bedrock. It looks like they came right from there, though. That's an interpretation. Mostly what we're doing here is observing. You can draw on top of a diagram like this to make it make more sense over time. So we have 6 different units starting at the top, and then the fractures are highlighted as well. The horizontal lines show differences in bedding. The colors show your main rock units. So layers is something I use interchangeable with rock beds. Fractures, and then there's 2 different materials that are loose pieces covering the slope. They came from different units here. This is larger, but it's also similar to the last diagram. We can make a few observations because it always starts with observations. In my work now, observation first, interpretation second, right? So let's see. We've got some red rocks. We have some staining on the outcrop as well. There are pretty vertical cliffs versus more gentle slopes. Like I can't walk straight up this, but carefully I might be able to walk down that. There are different ledges that appear to be layering, and then angular corners and vertical fractures as well. Just like in the last diagram, we have loose pieces at the base versus solid rock further up. So let's think about observation versus interpretation. So an observation would be there's loose rocks on the slope. The interpretation is that the rocks are there because they fell off the overlying cliff. That makes sense. We can observe that rocks are red here, and the red color indicates that the rocks were likely deposited on land because of the presence of oxygen. It leads to iron oxide, which is typically red. You could sketch this, but we also have this slide where it's been done for us. I'm wondering if this sketch changes the way you view the previous photograph. For me, it makes a lot of things clearer. You've got ledges above the front cliff. You've got a reddish-brown cliff with fractures. We see reddish-brown layers, loose material, and angular blocks within that loose material. All right. We'll look at this volcano and think about if we were to sketch over this, how that might highlight a few different features. Let's try to observe it. Okay, so this volcano is a cone-shaped hill. We have magma coming from it here, orangish, yellowish. Over time, I'm thinking as it cools off, it gets kind of gray and silvery. So this is much cooler as it moves away. We have a nice little wispy cloud above the magma. The magma is thrown up into the air. A lot of it's falling back into the crater itself, forming this cone. Some of it's moving further away. So differences during the eruption result in smooth, silvery patches and then rough, dark areas as it cools further. This is a concept sketch, kind of summarizing everything we see here. Gases, that was the wispy cloud I mentioned. Magma, which turns into a lava flow and cools off over time. The volcano itself, with somewhat steep slopes, right? This is a good way of breaking down information and actually learning something from it, rather than just saying, oh, it's a picture of a volcano. We're breaking it down. And even at my level or my experience as a geologist, this is fundamental to everything that I do. Okay, we'll move away from volcanoes for now. Back to water. So where is the water in this diagram? How does it move? And how is it affecting the geologic features and surroundings here? See precipitation. I see glaciers and flowing water down slope, downhill. And then the ocean here. And ocean currents. So water moves from the surface to the atmosphere and back again, really. Raindrops form a thin film of liquid that coats rocks and soil and causes them to weather. Glaciers might transport sediment and carve the landscape and characterize it over time. Flowing water is going to carry sediment. It's really the most important sculpting agent on Earth. The upper parts of the oceans are constantly in motion with currents and with waves that erode and shape coastlines. Water accumulates in lakes and rivers. Water can also sink down into the ground and become groundwater. Groundwater can then emerge as springs or just be part of what we call an aquifer, where we get water from the subsurface. This concept sketch is kind of reflecting what we discussed in the previous block diagram. Okay, so you can simplify it this way, showing the rainfall moving down the surface, evaporating back up. Also mentioning groundwater, which also flows towards lower areas and then emerges again. So it's some of the same aspects of the previous diagram. It's just a huge simplification. We could also think of Earth in terms of 4 spheres: the atmosphere, the biosphere, the hydrosphere, and the lithosphere. Now, the lithosphere is the solid part of the Earth on top of the asthenosphere. We're going to just use this very broadly. The hydrosphere is water in all its various forms, including the oceans, lakes, streams, glaciers, groundwater, and water droplets and clouds. More than 96% of Earth's water is salt water in the seas, and most fresh water is in glaciers and groundwater, not lakes and streams. Although Michigan has so much fresh water in the lakes that surround it. In the atmosphere, gases are what surround Earth, mostly nitrogen and oxygen. That includes the air, clouds, and precipitation. The biosphere is life in all the places it exists on the land surface, in the seas, in the air, and below the ground. So any of the life on Earth. This is not to scale, but hey, we're zooming way out. This is Earth's place in the solar system, with the sun, of course, at the center of our solar system. It generates its own light. All the planets are bright because they reflect the sun's light. Mercury is hot, but it has almost no atmosphere. Venus is quite hot, but it has a thick atmosphere that causes a greenhouse effect, trapping heat within. Earth, our favorite, I hope, has water, clouds, and life. Earth's moon is covered in craters, and it's the reason for the tides, the pull of the oceans on Earth. Mars is smaller than Earth, and it might have once contained liquid water. I'm not up to date on that right now. It seems to always be changing. We have asteroids as well. Those are fragments left over from the formation of the solar system. They're now concentrated in orbit between Mars and Jupiter. Jupiter is the largest planet in the solar system, and it's composed mostly of hydrogen and helium, like the sun. Saturn is like Jupiter, and it has rings that are composed mostly of small chunks of ice. Uranus and Neptune are bluish green because they contain methane. And Pluto, a long time ago now, has been reclassified as a dwarf planet. There are other objects just like it further out. The orbits of Earth and other planets are nearly circular. Distance from the sun doesn't cause the Earth's seasons. We'll get into that later. All right. We'll talk about how geology is expressed in the Black Hills of South Dakota. Just observing, we have mountains surrounded by curving ridges. Rapid City is on the east side here. If you were to cut a cross section through this whole thing and look at the subsurface, we slice it and look at the side. We have at the center an uplift of older igneous metamorphic rocks with younger rock layers tilted away from that range and eroded. They don't exist there anymore. We have famous gold deposits that were formed by submarine hot springs, hydrothermal rocks, and later burial and metamorphism nearly 1.8 billion years ago. Mount Rushmore, the faces that were chiseled into that are into a granite that solidified in a magma chamber 1.7 billion years ago. And the uplift of this right here, granite and the surrounding metamorphic rocks, that happened 60 million years ago, and it changed the sedimentary rocks, which were previously pretty flat over top. It pushed them upward and there was erosion. So we'll zoom in on Rapid City. That was originally built on gentle slopes, which is one of the best places to live, I would say. Pretty stable place to live. But it was adjacent to mountains and near a water supply, which is the Rapid Creek. So it has a good water supply there. The ridges that you see were formed by tilted sedimentary rocks. Geology, I mean, it's hard to say it, but it's like the geologic features here control where people live and what they do within the landscape. The upturned rock layers that form that ridge divides the city. The Rapid Creek drains the mountains. It's a preferential flow path through the city. There's plains that are located east of the ridge with sedimentary rocks, some of which were deposited from a huge inland sea a long time ago. And then a small dam was installed along the creek that failed, I believe, catastrophically in 1972. The point is here that all these different geologic features control how we interact with the landscape. And we'll stop there for today.